Hey, thanks everyone. Can everyone hear me all right? Okay, great. So my name's Joe. I'm from, I work in Cambridge, UK at the Laboratory of Molecular Biology. And today I'm going to talk with you about differentiable molecular simulation and a software package in Julia. And this is the main focus of my research. So what is molecular dynamics? I'm familiar that not everyone here is a computational biophysicist. So the idea is you set up a physical molecular system, you define the rules of how the atoms interact, and then you basically just press play, if you like, which in numerical terms means you're integrating Newton's equation of motion, F equals ma. And typically, if you want to simulate biomolecules, this is very computationally expensive. And there are a few shortcuts. I think it's fair to say that MD has really helped us understand many processes in chemistry and biology. It's often used in tandem with experiments, so either improving models based on experimental data, or going the other way, suggesting what experiments to run. And I think it's fair to say that these methods are going to develop more and more in the coming years, because we have ever-improving compute, loads of cool machine learning, and better protein structure prediction. So what software is available? Well, there's a number of really very good mature software packages for MD. And they're all quite similar in the sense that they have low-level, fast kernels to run the computationally expensive parts, typically in C, C++, CUDA, Fortran, OpenCL, that kind of thing. And then typically they'll have a layer on top that you can interact with. So in the case of GROMACS, that's binaries and configuration files. And in the case of OpenMM, that's a Python interface. But that means that these packages are hard to interact with all the way down. They're often hard to kind of reason about and understand, often hard to customize. And there's no mature package which has support for differentiable simulations, which I'll explain in a bit. So what is Molly? It's a pure Julia implementation of molecular dynamics. You can think about it as one language all the way down. It's 100% Julia. And so the simulation scripts are just Julia scripts, which is quite nice. It's closest in design to OpenMM, which, as I said, has a kind of Python API. And then under the hood, OpenMM has a CUDA kernel, an OpenCL kernel, a kind of a fast threaded CPU kernel. And it lets you define potentials, simulators, etc. And the idea is they should be easy to define, and they should be just as fast as built-in features. And that's kind of analogous to the way Julia works. Most of Julia standard library is written in Julia because Julia is fast. And so it's the same philosophy here. So it's under active development. It's not stable or fully covered by tests, but we put a very strong emphasis on testing, and currently we can simulate standard biomolecules with the trajectories matching OpenMM exactly. So I've just got a list of features. For those who aren't so familiar with this type of software, it won't mean too much, but we've got this kind of standard non-bonded interactions and bonded interactions. There's some support for reading in setup files. We extend the atoms base interface, which is part of the kind of Julia ecosystem to share atomic data. We've got various integrators, simulators, energy minimization, various thermostats for temperature coupling, and then you can simulate in cubic or triclinic box with periodic or infinite boundary conditions. You can log properties throughout your simulations and various other bits. One nice thing is the unit-full compatibility. So this is a nice Julia package where you annotate quantities like a number, a float with units. And then if you try and add 2 units, it will do a conversion if it needs to, if you're adding a gram to a kilogram. And if you try and add a gram to a meter, it will shout at you because that's not allowed. And so that we actually use unit-full quantities within the software itself, which is quite nice for catching bugs, and indeed it's caught many, many bugs because it forces you to be dimensionally consistent. And we also have some basic visualization with GL-Machier. And it can run CPU, it can run threaded, and it can run on GPU, which I'll talk a bit more about. At the minute, there are a few things missing, so we don't have constrained bonds and angles, but by constrained, I mean constrained in the actual integration. U-old summation is the next big thing to add. Various other things. It's not API stable yet, so things will change. And yeah, we're missing high test coverage, and we're missing extremely high performance, which I'll come on to later. So just to give you an idea of how the code looks, you can define components individually. So here we just set up a boundary condition, set a temperature, and you can see there the example of the unit full quantities, just annotated on the end of the floats. And then you set up some atoms, some coordinates, some starting velocities. We want to simulate with Lennard-Jones, which is a simple pairwise potential, and then we just set up a simulator and press go, basically. And this visualize function gives you some quick and dirty visualization built on top of GLMechio. And if you want to run a simulation on a biomolecule, such as the one on the right, you can use the more kind of wrapper-like functions. So you can read in a force field file from an XML format, and then set up the system based on a protein databank file. And then typically in this case, you would minimize the structure, which you can do, set up some random starting velocities, and then simulate with the Longevin dynamics, which is a stochastic simulator. And that gives you something like what on the right. Okay, so I mentioned differentiable molecular simulation. This is kind of the topic of my scientific research, as it were. So the easiest way to motivate this probably is as an analogy to a recurrent neural network, which some of you are probably familiar with. If you imagine you have a sentence of words and you want to classify whether it's a happy or a sad sentence, you can think of this model going over each word in turn and updating its kind of hidden state, and then at the end you compare your hidden state to so you compare the output to the true output, which you know from labeled data, which gives you a loss function. And because you've implemented this in some amazing AD framework like Enzyme, you can just click backward and it gives you the gradients of that loss with respect to the parameters. And so differentiable simulation is actually quite similar. You have your starting coordinates, you run a trajectory according to Newton's laws of motion. So every step you can think about having coordinates and velocities. And at the end you have you generate some loss function. So in this case it's just root mean square deviation to the native structure, but you can have any kind of complex loss you want. And then you do exactly the same thing. You click backwards and you get the gradient of that loss with respect to the parameters of your force field. So those sorts of parameters are, how strongly does an oxygen interact with a nitrogen and the like. So if you wanted to learn a whole force field, you can imagine starting off with no interactions, and so your atoms might fly away according to their starting velocities. And then over training, you would learn to stabilize the native structure. And eventually, it turns out you can learn force fields for proteins, which you can check out in that paper if you want to. And really, I think the attraction, well, there's two. One is that you can train all the parameters in the force field at the same time, which is the power of reverse mode AD. And it's something that's missing in every other parameterization approach for force fields. And then the other attraction is the variety of possible loss functions. So you can treat as a loss function anything which you can calculate from the trajectory in a differentiable manner. So radius hydration, which is how extended your molecule is. You could look at interactions of different components. You could look at radial distribution functions, flexibility, et cetera, and in the last one, we're seeing an explosion of cryo-electron microscopy data, and you can fit to experimental data as well. So what software exists specifically for differentiable simulations? Well, some packages do exist. The best known is probably JAX-MD, obviously based on JAX. It's a really nice package. You've also got TORCH-MD, which has some support for proteins. And then in the broader ecosystem, you have kind of some packages related to physics-based modeling and even physical rendering. We heard some already at this conference, which is kind of related as well to this aspect. So Tai Chi is one example. And these are all promising, they're all great, but they're limited in some way by scope or performance. And so basically I'm trying to do it better with Molly. So Molly can do these differentiable simulations, including on proteins, and that's really the focus of its development. Okay, so what are the challenges associated with differentiating through a long simulation? Well, I expect most of you are familiar with the trade-offs on this slide. Certainly between reverse and forward mode, we've heard them in almost every talk, and they apply just as equally to molecular simulation. You would typically have a lot of parameters, probably more than 100, potentially more than 1,000. So that does point to reverse mode as the way to do things. But the big disadvantage with reverse mode over millions of steps, and anyone who's tried to train a really deep recurrent model will know that you do run into memory problems. And there is a kind of third way for these physical simulation methods, or for anything which is a differential equation, which is the adjoint sensitivity method, where you can solve an augmented ODE back in time. And I think that's very promising. I think that may eventually become the way to do this, but at the minute there's very limited implementations and guidance of that, specifically in the area of physical simulation. So GPU memory, so yeah, when you're training, let's say you run a 1,000,000 step simulation, you either have to store 1,000,000 kind of snapshots of the coordinates and velocities on your GPU, so that the tape can do the AD backwards, but that's obviously not going to happen because GPU memory is quite limited. So you have to think of ways around that. So you could use forward mode, as I said earlier. Gradient checkpointing is kind of the obvious way to do this. Every, say, 100 steps or so, you just store your coordinates and velocities, and you throw out everything else between, and then when you come to do the reverse pass, you recompute the trajectory. And also there's some possibility of doing this with invertible simulations, because some molecular simulations are invertible without loss. But it's worth pointing out that this is not a problem when you actually use the learned potential for simulations. When you get out a trained potential, it's just something you can use in GROMACS or in LAMPS. There's no performance overhead for storing memory. So this is just an issue with training. Another issue to deal with is exploding gradients. So as I'm sure we're all familiar with, AD gives numerically exact gradients, but it gives those exact gradients with respect to the actual numerical integration, not with respect to the physical simulation that you're trying to model. And that can lead to problems. If you imagine you have a particularly hard potential, for instance, a hard sphere potential with billiard balls bouncing off each other, those can give exploding simulations just running forward mode. So you have to do clever simulation methods there. But certainly with when you're doing AD through these simulations, they can really be prone to explosion. And so there's issues that have to be addressed that people haven't really studied yet, such as which integrators are best for taking gradients through. Do you require a more conservative time step than the normal simulation? Fortunately, there is quite a lot of work to pick up on there from the deep learning community. So there are also specific algorithmic challenges. So long-range electrostatic summation is one which we haven't got currently in Molly, but we aim to do this in the next year or so. These algorithms are hard just to implement normally. They're even harder to implement on a GPU, and to implement them differentiably in a fast way, I'd say is probably exceptionally hard. So that's kind of a real challenge. Bond and angle constraints. So the idea there is, instead of having a force to keep two atoms at a certain distance, you just say these two atoms are fixed to be this distance in the integrator. So every time you do a time step, you then basically move them towards or apart, which is trivial if there's two atoms, but when you have an atom in more than one constraint, that's non-trivial. So that's another algorithmic challenge. Stochastic simulations. So often you would use random number generators to basically model the bumping of external particles to keep the temperature constant. So that's something we have to deal with. Fortunately, there are some benefits, some things which you don't have to care too much about. So for instance, a crucial part of molecular dynamics is calculating neighbor lists. So let's say every few steps, you would work out which atoms are in proximity, which then would let you run a few more steps without having to recompute the whole n by n distance matrix. And because that algorithm is distances in and, if you like, integers out or booleans out, the gradients are flat everywhere. So that's effectively non-differentiable, which is quite nice. So I said we can do this. The history of this in Moly is up to now, and by now I mean the last 2 weeks or so. We've used Zygot, which is a really nice package. It's one of the, I guess in Julia terms, it's actually quite old now. And that uses internally forward diff as well to speed up broadcasting. I won't go into exactly how that works, but that works in the sense that it matches finite differencing for the gradients for reverse and forward mode AD. But there's a significant problem with this, which is that you can't mutate, and you also can't differentiate through CUDA.jl GPU kernels. And so that means that at some point you have to broadcast over the whole of the neighbor list, or you have to do some other clever chunking of broadcasting over the neighbor list. But you basically have to hold significant parts of the neighbor list in memory as you broadcast over them when you really just want to mutate. And that leads to poor memory usage and GPU performance. So recently I've been working on taking the slow bits, which is basically the force summation, so looping over atoms and adding the forces, and rewritten them to use mutation and as CUDA.jl kernels. And the AD for these is carried out with Enzyme. So at this point I should say, big thanks to William and Valentin for really supporting this and fixing many bugs that I've been reporting. So currently this is on a branch, and when a few things get ironed out and a few packages get released, this will get merged into main. But it basically, as of last week, this works, and it's pretty fast. And just to give you an idea, for those who aren't familiar with CUDA.jl kernels, it's kind of you can think of it as a high-level interface to a low-level thing. So it's an easy way to write native GPU code. So this is just this is like a really stupidly simple CUDA kernel, where you just literally, each thread just picks one pair of atoms that are neighboring and just calculates the force and just atomically adds them to the force vector. But actually performance is kind of all right. It's about 5 times slower than the equivalent in OpenMM, but the equivalent in OpenMM is about 1,000 lines long, and it uses incredibly clever ordering of neighbors to avoid blocking on the atomic addition. So this is this is like less than 20 lines, and it works pretty well, and it's differentiable with Enzyme. And Enzyme is the only way to differentiate through, to my knowledge, to differentiate through Julia CUDA kernels like this. So the next challenge here is to basically rewrite that 1,000-line OpenMM CUDA kernel to get this extra speed. So currently, you can get about a nanosecond in about 14 hours or so. These kind of rough numbers for a solvated system, and it's faster if you want to use implicit solvent. So I've just got some example gradients on the right there. So that's saying if you increase the sigma parameter on a nitrogen, then the root mean square deviation to the native structure over the simulation increases. And so with this version of the software, it's achievable to improve these implicit solvent force fields, which is what I'm doing in my research. And with further optimization, with another kind of 2 times to 5 times, which I think is eminently possible, we can target explicit solvent force fields. So this is ongoing work. Development's currently very active. We've had a couple of GSOC students, for instance, and yeah, as I said, the focus for development is going to be the force and energy summation. It's going to be U-old summation methods. And also we do need to develop an ableist algorithm at some point, which doesn't need to be differentiable, but does need to be fast. And in this autumn, I'll be advertising for postdocs and PhD positions to start my group. So if anyone's had their curiosity piqued, then do get in touch. If, even if you don't have computational biophysics experience, I'd be really wanting to talk to someone who has either GPU experience or kind of enzyme experience. So I also said I'd kind of talk about some lessons that I've learned the hard way, if you like, from taking gradients through long simulations. Controlling temperature is important. It kind of acts as a regularization. and various methods to do that seem to work. Initially, I was a bit worried about stochastic simulators because it kind of offended the idea of taking exact gradients and then ruining them by throwing in loads of noise. But actually, I think it's fine. Stochasticity seems to have a regularizing effect on both the simulation and the gradients. And actually, you should anyway be sampling over different starting conformations and velocities. So you should be getting a gradient distribution anyway. So there's no harm in taking that as part of the simulation itself. Norm clipping, or clipping gradients is basically essential. So the idea there is every 10 steps or 100 steps or whatever, you just look at the basically the kind of the magnitude of the gradients, and if it's too big, you just scale them all down. It's kind of a hack that RNNs use to avoid explosion, because by entropy your gradients would just explode over 1 million steps. They but one lesson learned the hard way: make sure you clip the gradients equally and sanely. Do it properly. Don't clip some and not others, because you will waste months worth of simulation. So yeah, my setup at the minute is to run reverse mode AD with checkpointing every 100 or so steps and clipping every 100 or so steps. That seems to work, and you can basically run. I think you can basically run arbitrary length simulations with this. I haven't run into any problems. You could run forever if you had the compute. Forward mode AD is actually not necessarily good here, because remember, the mature software is just really absurdly fast. And so you may as well just do finite differencing with the mature software at this point. Maybe if Molly gets to a point where it's, say, 2 to 5 times slower than the mature software, then forward mode AD becomes achievable, because when you do finite differencing, you do have to run, obviously, multiple versions of the forward pass. So it seems that float 32 and 1 femtosecond time step seems okay. That will probably not make too much sense unless you're deep in MD, but it seems that you don't need to have super high precision and lower time step. But again, I'm still kind of working on that. Getting gradients is pretty fiddly. You do have to play around with things and debug stuff. So it is only worth it over finite differencing if you have a lot of parameters. And yeah, the golden rule: just always test against finite differencing, because just assume that if you haven't tested against finite differencing, it's wrong, because it might be. Okay, so I guess I'd finish with some challenges for Enzyme, some things which I would really like to see come in at some point in the next few years. So probably the top one that would really help, I've spoken a bit with Valentin and William about this, is mixed CPU-GPU programming. So the idea here is Julia lets you do this really generic GPU style of coding, where you just have array dot plus other array, and that works on CPU and it works on GPU. But that doesn't currently work with Enzyme, because it's what you would call heterogeneous programming involving both the CPU and GPU. And the rule system, I believe, has just dropped. So I think that maturing and integrating with chain rules, there's the chain rules ecosystem is great. There's loads of rules floating around. So it would be great if they could become integrated somehow with the Enzyme rules. And those two things being fixed would allow Molly to use Enzyme as its main AD. So instead of having what we have at the minute, which is Zygote and then Enzyme for the slow bits to make them faster, we could have Enzyme for the whole thing. Also, it'd be nice to have an easy way to call Enzyme inside chain rule R rules, including for GPU kernels. At the minute, you do have to write a bit of boilerplate, and then continued support for GPU programming to fix any bugs that arise, which I expect they will, just because of the complexity of some of these algorithms. And so just to finish, I thought I'd show all these simulations were with Molly. All of them are also visualized in Molly, apart from the first one. And you can take gradients through all of these simulations. Whether those gradients are meaningful is a scientific question still to be addressed. So thanks a lot to the Molly contributors, and all the Julia contributors as well, and package authors, Zygote in particular. Thanks to William and Valentin for help with the Enzyme stuff. And I've based a lot of the implementation off OpenMM and GROMACS, and then the group I'm embedded in at the LMB, the George Shearer's group, and then previously at UCL I was in David Jones' group, who let me work on a lot of this stuff. And finally, thank you for your attention.
Thank you. Are there any questions?
I have a bunch. So how many
particles can you actually do in Molly.jl right now?
Yeah, so if you're just simulating without gradients, you can do quite a lot. I don't know the top number, but you'd be limited by GPU memory, but you could certainly do 10,000 no problem. If you're doing gradients, with the old setup, the Zygote setup, you'd be limited to about 3,000. In fact, this example here, the alanine dipeptide, which is a tiny molecule, by the way, it's just got a lot of water around it, is probably the limit. With the current setup, I still need to benchmark that, but I expect you could probably go to probably about 10,000, yeah.
But you are running on single GPU right now, is that true? So
Single
are you
GPU.
thinking of moving to, let's say, I think MPI.jl plus CUDA.jl then to do multi-GPU at some point, or?
I mean, yeah, I'd have to skill up a bit on writing multi-GPU kernels, but provided I did, then there's no reason that couldn't happen. I don't know if Enzyme supports multi-GPU gradients.
We support MPI in theory, right? So, I don't know.
I mean, either if you don't use MPI. So you can either use, I got that. You can either use MPI.gl, and then you basically say you cast your program as a traditional MPI program, and that allows you to scale up to many GPUs. But if you there are simulators where you say, I'm just going to do shared. I have 6 GPUs in my box, and I want to use that. There might be some interesting questions around the CUDA memory model eventually, but modulus that should just work. Cool. I don't see, you need to come up with a partitioning, right? That splits the data across your GPUs.
Yeah, yeah.
So a lot of the recent, let's say, flagship computational bio plus ML stuff also used machine learning potentials for MD.
Yeah.
Have you considered doing something like NeckWhip or Allegro with Molly? I mean, speaking to some of the NeckWhip people, they had a lot of issues where they had the machine learning potential, then they spent months just getting the torch script interface to, I think it's lamps in that instance, just getting it right. But in theory here, it should be a lot easier for you, right? Because you could work in just one language and avoid having this torch script step.
Yeah, I think that can work. There was someone who was going to look at that. I need to follow up on that and maybe try it myself. But I think you could write a fairly simple Flux model. So Flux, for those who don't know, is a kind of deep learning library in Julia. You could write a fairly simple Flux model to run Equip, for instance. And obviously Flux is differentiable with Zygote, and this is currently running Zygote. So yes, that would work. The issue with that is that the memory requirements are severe because an Equip Allegro type model is, although it's actually not massive as neural networks go, there is significantly more memory to kind of store and cache in there than a single force evaluation. But I definitely would like to look at that,
An additional point, the project in which Joe and I are collaborating, mostly Sesmix, there are people who look at machine learning-based potentials, and I think the biggest challenge would be actually to get the S3 groups and invariants and all of that hidden magic that is underneath NeckWhip and Allegro actually working, and that was non-trivial the last time I looked at. Those implementations are special.
Like in the sense that sorry to follow up on this, but like in the sense of you not having implementation of the equivariance groups in Julia right now. Okay.
It is worth saying for that a lot of those models are becoming more simpler over time. So there's a flavour of models called the ACE models and linear ACE, which kind of throw away a lot of that equivariance in favour of pairwise or more linear features. So there may be a route there to...
and ACE has a Julia implementation.
It does already have a Julia implementation, yeah.
Any other questions? Comments? Then let's thank the speaker again.